So welcome back to Virginia Tech, everybody. So we'll go through the syllabus today. I would like to kick things off with an example and can tell you about inference itself. And so if we don't get through all the logistics this time, we'll run into it next time. So I'd like to say something about statistics today. So thank you for everybody being of the utmost privy to the health standards. I think this is old hat for us, so the mask thing. Can everybody hear me? Okay, I'll try to be as audible as possible. Also, because we're in a variable situation and we have to stay fluid, I'm going to be recording all of the lectures for you. I also have all the lectures recorded from the last couple years. And so while this class is a little bit stochastic, it's about what you see in Casella and Berger, and that'll be our textbook. So that's standard fare for all of us. If you don't know what that book is and you haven't looked at the first 5 chapters of that book, that's what you will want to do first. Is so start working through probability theory and make sure that you're up to snuff on that. This is a sequential class. It segues after probability. So you can't do statistical inference without already knowing something about probability theory. And so I'll try to hone you in on things that you should know. And there's a possibility that this isn't the course for you. And so if you haven't had probability or some statistics class where you invoke some linear algebra or calculus, and you've never heard of a normal distribution or a uniform distribution or a binomial distribution, you are in the wrong class. So this is, I would consider, one of your more hardcore statistics classes. And it's a little bit challenging in terms of the scope of the mathematics that we cover because we bounce all over the place. So we're covering a very broad topic, statistical inference. So somebody please help me out and tell me what this is. What is this class even about? What is stat inference? And if you don't know, you're in the wrong profession. And I'll try to make sure that we all have coherent definitions as we move through. But you should have some inkling. Somebody help me out. What's stat inference? What is this? Yeah, please, Eric.
I would say drawing conclusions about a population from a sample of data in the light of uncertainty.
Yeah, something like that. I mean, you are always in the darkness of uncertainty or the light, depending on how you quantify that uncertainty. But it's basically drawing conclusions from data, and that's what it is. So things you don't know, you're going to try to learn from data. I have a problem down here at the bottom of the board. So what this says is I get to see a sequence of data, n data points, xi is going to be uniformly distributed from 0 to theta. So there's a probability distribution. And I can answer all kinds of things about this probability distribution, and I can do it wildly uncontroversial. I can tell you all kinds of properties of this distribution. And if I couldn't do math, I could probably work with a computer and approximately tell you as close as you wanted to know. And there wouldn't be a lot of wiggle room for answers. Stat inference is not that way. It's the inverse problem to this, and it is a harder problem. And it relies on everything you know from probability. So let me just show you what this distribution is real quickly before we jump into logistics. There's some value theta, so this is a distribution. This is telling you the support of this distribution. It lives between 0 and theta. I didn't tell you theta is positive, but a little bit about my convention. This is over to the right-hand side, and it's expressing an interval. But I should be polite and tell you that theta is positive. I would probably want to make it greater than 0 if it were going to be a real problem. Because if this is a uniform distribution from 0 to 0, there's not a whole lot of variation there. And so any child could answer what they think theta is if they just got to see repeated draws and it just showed up as 0, 0, 0. If this was a real continuum, and I saw 0 twice in a row, I'd just stop. And I'd say there's either something incredibly wrong with this problem or I already know the answer. Because the probability of seeing 0 twice would be 0, and I shouldn't see that. So there's a value theta over here. in the distribution, the density of the distribution was 1. And that's the height. So I would call this fx given theta, where this is a uniform. This is the density function. And what this means to sample uniformly from this uniform distribution, so we're invoking some words there, and I'll tell you what they mean in an IID fashion. Somebody help me out, what does this mean? IID. Independent and identically distributed. What that means is that the realizations xi's don't depend on each other. There's no influence on each other. So let me just ask you a question. If I got to see a draw x1, let's say it wound up right here, and what this line is expressing is the density of the sample points that I expect to see as I sample, and they're uniform. So I expect to sample uniformly from this. So, is this point right here independent of that point? Presumably, by the way that I've shown this to you. So what does that mean? Does it mean, can I learn future x's after I see previous x's? So do I know anything about those x's? Let's just see if I sample a whole bunch of these. So let's say x3 was there, x4 was here, x6 was here, so on and so forth. And I'll say that's n, whatever that number was. And I could draw a histogram of all of these data points, and it might look something like this. So, roughly speaking. So I could draw a relative bar chart to express the patterns of these data points. If I didn't get to see this distribution right here, if I didn't tell you this, would you have learned anything about future data points from the draws that we just acquired? Let's just imagine I just drew this histogram for you and I didn't tell you this up front. Am I telling you something about future data? I am. So it's kind of an interesting question. Did the previous data tell us anything about the future? And you're inclined to believe because of the independence. So this is independence. And identically distributed. Stuff you should know already. Does not mean that the data points don't have any information about the future. They clearly do. If I didn't tell you this right here, that I have a uniform distribution between 0 and theta, I would start to learn about this right endpoint, theta, because of all of this. And I would also learn that this stuff looks approximately uniform. And I could start to make guesses of what other data points look like. So I might ask a question, is it likely that my next data point would be over here? And I would probably say no, because there would be a huge gap between what I've already seen. Unless it was some mixture and I wasn't sampling in an IID fashion. So what it means to be IID is given information about the distribution. If you know the distribution and you know its parameters, i.e. you know this value theta, then the previous data doesn't tell you anything about the future. And so the data tells you about the future. We use data to forecast all the time. And so if data didn't tell you about the future, previous data, predictions we wouldn't be able to make them. And so what we're doing is we're learning about the distribution. And if I knew what the distribution is, then the previous stuff doesn't help me to learn the future. And so there's a difference. So I say this stuff is conditionally independent. And there's a difference between marginal independence and conditional independence. Conditional independence saying conditioning on the parameter set and the distribution at hand, then things are independent. And so let me just distinguish these two things for you. This is what you would learn in a math class. So in math class, I'll call it probability. Probability isn't about inference. It's about probabilistic properties, the random nature of this data that we have observed. In probability, we say something like this. Xi is independent of Xj. So this is the independent side. This means something like this, that the joint distribution of x1 and x2 factorizes. We could write this out a little bit different. Most of us will know this probabilistic property, and if you've never seen this before, you're probably in the wrong class. So this is not true for data. This happens in sets, when I know everything about the space. So data doesn't behave this way. And I'll tell you what we're missing in a second. You may think, oh, it's just your notation, but I want to dwell on the notation and make sure we're expressing the right things and thinking about it correctly. Or I could write something like this. F of x1 given x2 is equal to f of x1. So this is the probability density of x1 given x2 doesn't have anything to do with x2. So this means given. Or conditional on. Lots of different synonyms that we could use. And so how do we get this from the other thing? Well, maybe you know something like, I call it Bayes' theorem because it's an application of this theorem, but you might just call it a probability rule, the definition of conditional probabilities. And whether or not this is a discrete probability distribution or continuous, this rule holds. And so it says something like this. So this thing is going to be f of x1 and x2 divided by f of x2. So that's the joint distribution divided by the marginal distribution. And so hopefully you've learned something about that when you know these definitions. If this is true, right here, then this says f of x1 and x2, the joint distribution factorized. And I divide it by the margin on x2, it cancels, and it's f of x1, and that's what that says. So these are equivalent statements. And so presumably you know the rules of probability, and you could prove all of this to me. We're not going to do all that in this class. We're going to use these things that you should already know. And so this doesn't happen with data. So because we learn from data. So if I just started seeing somebody start building this histogram, I would be learning from it. And I could probably say something about the future. We'll study forecasting later on in this class, and we'll see how to exploit it. Conditional independence is a little bit different. It's almost the same thing. But there's a stark difference for me as a statistician. I used to think to myself, well, if data is independent and the past doesn't tell me about the future, then how do we learn? And so obviously it has something to do with it. What we're learning is the distribution. Because usually the hand of the statistical gods don't say, oh, by the way, here's your distribution. So you have to build that in the first place. So my fiction in this class is that we're going to get to know what the sampling distribution is. And I'll teach you properties of inference. And later on in a modeling class, you'll have to build your distribution, then do your inferences, look at residuals, things like that, and modify your distribution. And so make sure it forecasts well and does all the things that a distribution should do for you. So this is conditional independence. Very similar. It says xi given theta is independent of xj given theta. This is a bar. right here. So this is my set xi given theta. And what that means is f of x1 and x2 given theta factorizes. And the other one is true as well. F of x1 given theta and x2 is equal to f of x1 given theta. And that's if they're IID. So given that I know theta, everything factorizes. Now you might just say, hey, I already knew that. But there is a difference between expressing marginal independence and conditional independence. And so the marginal distribution does not factorize. And I'll show that to you later on. So the data does not factorize, but in the presence of the parameters of the model, and assuming that this f expresses a uniform distribution, then everything factorizes, and we can exploit that. And so IID is also known as simple random sampling. And so what it means is that given the distribution, we get these properties, i.e. factorization. The information is not helping us, but it's in the presence of the parameter. So given that I get to see the parameter, this value of x2 doesn't help me. I already know everything there is about the distribution. And I'm not going to learn anything by giving you x2. So it's kind of like if you go to a casino, you play roulette. I'm going to assume that people know what this game is, but it's the game with the wheel. And it has red and black spots on it. And you spin a ball, you take a ball and you run it over the top. And anybody that's ever played roulette should jump on that and say it's the green things that are important. So, because that's where the house wins. And so they don't give you equal odds of playing. They take a little bit away for themselves. And so if you're betting on red or black, where the ball lives or lies in each one of those tiles has a number on it. If you pick red or black and it shows up as green, of course you could pick green if you wanted to. But if it showed up as green and you picked red or black, you lose your money. And if there's two green triangles on the roulette board, you shouldn't play that one, unless you just love variation. Yes, I'm losing money in this fun way. So I've done it. So usually I walk through a casino when I'm there, I'll throw $40 on like red or black or something. Let's go out to dinner maybe. So, or not. So, something like that. If they didn't tell you where the red and black were and the size of the triangles and what the probability of landing on each one was, then watching the board and seeing what came up, red or black, would help you. However, in places like Vegas or Atlantic City, we know what the probabilities of the boards are. So we know how many tiles, we can go and inspect them, look at symmetry. Hopefully they're not using any magnets or anything, but that's illegal. So we assume that it's just a random roll. It does turn out certain rollers can produce certain effects. So you have to be careful for that. So we probably don't know which way they bias everything, but it's interesting. You can try it yourself, flipping a coin or whatever. You can train yourself to land heads. So just by the height of the flip. And so I know people that can do about 9 out of 10 heads compared to tails, even though when we do it and we just randomly flip it without any practice, it's about 50%. It's not quite, it's 52-48. If I told you what all the spots on the board were, and I told you the sequence of reds and blacks, you wouldn't be learning anything. They usually get you with that. So everybody knows that if you're staring at, well, there were 5 reds in a row, the probability of there being another red is extremely unlikely. But that previous draws of all those reds didn't influence the future. You already know the probabilities. That thing is just to bait you into thinking you can figure something out. So, but you already know the probabilities, so it doesn't help. So there's something to distinguish there about what the difference between independence and conditional independence are. So data, at best, is conditionally independent. And so I would even say dependent models, they have conditioning on how they depend. And so we can even come up with factorizations of dependent models by conditioning on the right stuff. And I'll teach you how to do that in this class as well. Any questions before we go into a little bit more detail? I don't expect that to be a highly elusive concept, but I do understand sometimes people struggle with things that they've learned in the past. So when I was an undergraduate, somebody used an example of a basketball player going to the free throw line and talked about their shots being independent. And I thought, no way. And I wasn't harping on the nature of the game, the independence of it. I know they wanted to use it as an example, but I said the shots are only independent if I know their probability of making the shot in the first place. Because if I saw Eric go to the free throw line, what do you think he could do? What percentage? 30, something like that. That's pretty good. Obviously, you're going to inflate that a little bit, right? So he's really like 15, you know? But if I saw somebody like J.J. Redick, my old college hero playing basketball, or if you don't like him, that's fine, 92%. But if I watched Eric go to the line and shoot, and he's making his 30, or if I watched J.J. go to the line, and he's making his 92, if I didn't know those numbers up front, I would be learning something. I'll try to express this to you in a simulation next time. So you learn if you don't know the parameters of your model, or what the distribution is. You learn the distribution itself. And there's uncertainty in that, and I'll show you how to propagate that uncertainty as well if you take maybe my Days class, which I teach next semester. Okay, so I think we know what inference is. We know these simple definitions of IID, simple random sampling. This is all in chapters 5.1 through 5.3 of the text, and you should get started on looking at that. Before we go into any more details, let me just ask a question. What are some major branches of inference? And some of you might be surprised to learn that there's more than one way to do statistics. There's a whole bunch of ways, and this is what makes this class challenging. Casella and Berger, Casella happens to be a Bayesian. He's passed away, so I guess in his former self, he was Bayesian. But he writes a rather classical textbook, and it bounces all over the place. So I would say he's about 20% Bayes in the class, and I'll try to hone it in at about that level, 20-25%. But there's all these other things that people do. And we want to learn about them, and we want to learn what's good, when do you apply, does it matter, which technique you use, and we want to understand all of those surrounding issues. This is a big problem because there's lots of statistics problems and different procedures performed differently. So, branches of inference. You might consider these schools of thought. Or different ways of doing inference. Somebody help me out. Let's name a couple of these. I'd be shocked to find out that you didn't know anything about different branches of inference. I'd also be shocked if you knew how to distinguish them completely. It's going to take you several years to really understand what's what. And so sometimes there's different ways to derive exactly the same thing using a different school of thought as well. And that's where things can get really complicated. It's like, well, what is it? It's more about how you did it rather than what you got. So somebody help me out. What's a branch of inference? Name one. I've already named two. Okay, yeah. So Bayesian. Somebody says frequentist. And there's different types of frequentists out there. There's relative frequentists, there's asymptotic frequentists. So there's frequentists that operate on your actual data set. And there's frequentists that invoke properties that assume if you took the limit of your data, i.e. n went off to infinity, then you would invoke these certain properties. Everything would converge to something that was maybe frequentist. I want to point out that there's a lot of overlap between these techniques. Bayesians can be optimal frequentists. So back in my day, these guys used to fight with each other, and it's because they didn't understand each other. And that's what we want to clarify in this class. We want to make sure if you use the term frequentist, you do not mean anti-Bayesian, because it doesn't mean that. Bayesians can be rather proper frequentists. There's no necessity to be a frequentist as a Bayesian, though. So there's a subjective school of thought as well. So there's different types of Bayesians. There's Bayesians that call themselves objective Bayesians, and the only thing I object to is the word objective, because whatever criterion they're objectifying or optimizing is subjective. You chose it. So maybe you have good reasons to be. There's also a branch of Bayesian thought called subjective Bayes. And probably the worst part of that is naming it subjective Bayes, because everything is subjective. So we'll talk about what those are. Anybody else? Other branches. These are the popular ones that people go. They usually think that these are separated, but we're going to make sure that you understand that there's strong overlap and what it means. Anybody else? I can wait. Why not?
I'm not sure what it's called, but I remember there was a guy, Dave Finetti, who changed one of the core assumptions of classical statistics of time velocity or something like that.
So Dave Finetti invoked something called exchangeability you might be thinking about, and he's getting rid of the notion of IID. And we'll talk about that a little bit later, sometime this week probably, maybe next week. And so he's going to loosen up the assumptions. So instead of saying data is IID, he's going to talk about properties of data, not properties of data with distribution in hand. And so the IID notion means that you have the distribution. So it's not just a data property, but it's a data with model property. And so to invoke the IID nature of things, you have to have the model in hand. But I might say for IID data, I can scramble it in any order, and that's true. That means it's exchangeable, and it has the same information. And so Dave Finetti liked to think along those sort of lines. Dave Finetti was a probabilist. He didn't do a lot of statistics, but if you read through his stuff, he's probably a Bayesian, and he considers it an all-encompassing branch of inference. And so there's a very important theorem that Dave Finetti came up with, Dave Finetti's representation theorem, that basically says you have a permission slip to model all of your data using conditionally independent distributions. You product them together and you do the things that you would normally do. So that's good. There's good basis for doing the things you would have done anyway. We'll talk about that a little bit. You said classical. I kind of like that. So let's start there. So, real quickly, what's a classicist? Who knows, right? It doesn't ever mean anything other than it's old. And so if somebody says they like classical music, you're usually not thinking that they like Metallica. So that's not what they said to you. So you're not quite clear. If you did know a lot about classical music, and I do not, you know there's a whole bunch of different subclasses, and they're different things, and they didn't all happen at the same time, and they didn't all live at exactly the same time. It just means it's the old stuff that's stood the test of time. If you survey the classics in literature, you're probably not reading Tom Clancy. So you're reading something older. And so all this means is it's old, and sometimes people overlap it with frequentist because maybe frequentist techniques prevailed at the early part of last century when statistics was unfolding. And this shows up maybe around the 40s, but doesn't get a lot of traction until the 60s. And then probably gets a lot of traction in the 90s because of computers. We could do the things that we said we wanted to do. What is a frequentist? This is the one that really bugs me when people give answers. I'll just give you a hint. It's something to do with the word, frequency. There's some frequency of something that you're controlling. There's something, a property that you're looking at that has to do with repeating the trial over and over and over again. And so when people say they're a frequentist, I want to know what they're monitoring. Frequency of what? And how are they doing it? So when somebody tells me they're a frequentist and doesn't add any more insight, I usually just think they don't know what they're talking about. You just want to use this term and say you're not a Bayesian. And that's not good enough for us anymore, because it just causes contention. What's a Bayesian? This one's a little bit easier, because all Bayesians do the same thing, but the way they do it might be different. Doesn't mean they all come up with the same inferences. They still build models. What it means is they use Bayes' theorem. So, and they infer things off of the posterior distribution, and we'll be talking about that. So in this class, what I want to do is I want to give you a lot of different techniques. I want to give you some asymptotic frequentist techniques. I want to give you some more computationally oriented techniques that maybe invoke some form of relative frequency. And I want to give you some Bayesian techniques, and I want you to compare them and see where they work and where they don't work. If we just study the textbook, we'll know how to do a bunch of math, but we won't actually understand how things work. So we might have these overly optimistic senses that, well, as n goes to infinity, everything works out. I'll tell you this, if n was infinity, we would know the answers, and we wouldn't need to do statistics. So for me, that's a little bit vacuous. I do like taking my arguments to limits to see what happens at the extrema, but I like to compare based off of what I actually have. And so in this class, I'm going to aim towards comparing things. So let's go through some syllabus real quickly. Hopefully we'll have time for a simulation. This is your web page for this class. Somebody had asked me yesterday, where's the Canvas page? I don't use it. And the reason I don't use Canvas is because they're going to make me change using whatever next year. It's been Blackboard, it's been Scholar, it's been Canvas, and I'm a statistician. I know what's going to happen next. It's going to be something different. And so I don't like changing my modalities all the time. I like things to be a little bit persistent, so I'm going to use my web page to host all of the materials, and I'm also going to use Slack. And so I'll be sending all of you that are on the roster in this class. I think everybody's been able to enroll in this session. I'll send you out links to all of this material. So I have your email addresses, and I'll have you an email by the end of today with all of these resources so that you don't have to memorize them all. But my web page is www.apps.vt.edu / my last name, which is Lehman. And that'll take me to this page. And I'll have that to you in a link so that if you can't read my writing or you can't see what's at the very top, that's okay. You don't have to rifle through my video trying to find it. And where you're going to go is you're going to click on that link right there, courses taught. There's my full name, Scott Lehman. Personally, I don't care what you call me, just be reasonably respectful. So, unless I know you really well. So, and then you can call me anything. So, here's all the courses that I've taught, at least semi-recently. The first one is yours, 5114. And so usually I have all my old materials if you ever want to survey classes. Last night I wiped out all my old materials from Inference because we're going to start anew. But again, everything is outlined in the old videos, and I'll show you where those are hosted in a moment. So Here's your course. Basic structure says to learn inference. So we're going to be covering inferential methods, which is lots of methods. So emphasis on plurality. We'll start talking about order statistics because they're kind of interesting and fun to play around with. We do use order statistics. So it's basically when you order your data and you look at the distribution of that ordered data. We'll look at approximate methods, delta method, asymptotic frequentist type methods, the old stuff. We'll see how well it works. So we'll cover techniques I like and techniques I don't like. And really the name of the game is to compare, and you'll decide for yourself when and where you want to use differing techniques. And the most important thing that you get out of this class is you have reasons. And when somebody asks you why you did something a particular way, and could you do it a different way, you can answer that question. You can say, here are my reasons, and you might say, I don't like that technique, and I can show you why, for this sort of problem. Or you might say they give similar answers, and it doesn't matter how you do it. So you can do it any number of ways. And it depends on the problem. And that's what we're going to learn. We'll learn a little bit about convergence theorems, not too much, but we'll be studying convergence. And if you're a PhD student in statistics, you'll want to pay attention to that stuff because PhDs should understand how things converge and make sure that they make sure their remainders and things like that are decaying towards zero. We'll have to study that very carefully. If you're an engineer, you kind of just want to code stuff up and see how it works. And so there's going to be different levels for different people, but I will stress PhD students in statistics will want to know kind of more the deeper math. But this class is supposed to be accessible to a wide variety of people. So I know you all have different backgrounds. We'll be studying classical Bayesian stuff, principles of inference, that's chapter 6 in the book. Computational methods, we'll be studying intervals, confidence coverage, pivots. We'll do a little bit of algorithmics as well, things like MCMC, a little bit. EM algorithm, so we'll study computational algorithms, and I kind of like them because they help us to actually understand all of these principles that we see all through statistics, design principles, inferential principles, so on and so forth. And they all appear in computational methods. So we'll be studying those. So that's just an overview. Here's your contract for the class. So I start out by describing the Virginia Tech standards. It's probably worth reading through all of these, but you've seen these in every single one of your classes for the last year and a half, or at least you're supposed to. So we're committed to protecting the health and safety of all members of its community. By participating in this class, all students agree to abide by the Virginia Tech wellness principles. I just saw yesterday, faculty are not required to boost or declare the vaccination status, however you are. If it makes you feel any better, I'm boosted, I'm double vaxxed, I've also been hit with corona twice. So I'm as good as you can get. So I can tell you all about it. So one of them wasn't too bad, and one of them ruined 2 weeks of my life, you know? So no big deal. Anyway, I adhere to these. You need to adhere to these. Face masks, you know the drill. So you've all seen these. I'm going to just move on through it. If you have any questions or concerns, let me know, and we'll figure it out. Objectives of the course, basically to understand both theoretical properties and computational properties of statistics. So not only understand how to do it mathematically, but understand how to do it on a computer as well. So we'll give a thorough treatment of statistical inference and not side with one of these paradigms too strongly. We'll be doing a constant comparison. So I will start my class, the first 3 weeks we'll be building up to doing comparisons that you see in chapter 10 of the textbook. It'll seem like we're running behind, but we're actually getting ahead. So when we hit things like chapter 7, we've already done it. So I'm going to stagger things a little bit, just so that we have some basis for why we're doing what we're doing. Okay, so logistics, you know where you are, you know what time it is, so we don't need to review that. I'm going to be doing evening review sessions, so sometime after 5:30. That'll happen about every 2 weeks when homeworks are approximately due. And the rules are going to be that you post your questions to Slack at least 5 minutes before we start the review session. I will survey the questions and I'll carve out a lecture for you. And so hopefully it's comparative. So what I don't like is just people asking me random questions that we can't do things in a way where I compartmentalize these 3 questions are exactly the same, but in different contexts, I'll put them together. And so I'll have a Slack resource page for you where you guys can ask questions. You can ask questions to the TA. You can ask questions to me. They can be logistical. They could be maybe more insightful where you're trying to get some grasp of statistics. You could point out an error that I've made. Sometimes when I need an errata, I'll go to Slack and say I made a mistake. And here's the correction, and we'll cover it next. So it's a place where we can have communication. There'll be a section for review sessions where you can post your questions. We will need to come up with a time slot for it, and I apologize in advance. With a class this size, I can't appease all of you. So we don't have the same schedules. And so they're there for you if you'd like to come. And in some way, they're a more beneficial substitute for office hours, so that you guys can hear each other's questions and interact with each other. I've done this a lot of different ways in the past. These will not be recorded, because then people won't come and they won't ask questions. And what I end up getting is a bigger left tail of my grade distribution. So that's what I've noticed. If I give you too many online resources, we learn worse. And it's no surprise. So the people that come to everything, I still see the people that are top of their class, they get hundreds on everything, but I don't want to see 8 of you struggling. I want you guys to get as much out of this as possible. So we'll need to come up with a time that we can use to do review sessions. I need to do them in evening just to open up your schedules a little bit and to make sure we have a room reserved. So for next time, I'd like you to bring in your calendars and we can decide on a time, and we'll do a couple rounds of voting to try to come up with something that works. You don't need to make every single one, so that's not compulsory. So this is there to help you. We'll also need 2 midterm days, so let's look at our calendars and make sure that we can schedule those. What I would like to do is I'd like to do one close to the spring break, our first midterm, and then one about a month later. And that's a couple weeks before the final exam. The easy one is the final exam. It's already allocated for us. So every class time slot has a final exam already declared for it. I don't choose it. Yours is 1 to 3 o'clock on May 7th, and it's Saturday. And as of now, I intend to do that in class. Of course, if we get hit by a surge and the university wants to pivot, we can do everything remotely as well. And so I have contingency plans for contingency plans. But right now I'm going to plan for an in-class experience, because I think that's what we all need, especially in a class that's this dense. So bring your calendars and we'll get those midterms down as well. Make sure you know when your conferences are. Most conferences I think are remote anyway, so you should be around. Also, don't schedule your plane flight home on May 6th. So that's something that's going to drive you crazy. So if you do that. So make sure that all of your travels are outside of these windows. My office hours are going to be the review sessions. After class, I'll always make myself available and by request. Usually I host, drop by office hours. If you need something, swing by real quick. We could probably answer the question. If you see me in the halls, ask me the question, and I'll try to answer it. If we need more time, then we'll sit down and we'll do it. So I'll try to make myself as available as possible to you in a meaningful and constructive way. I found that over the years, if I just schedule office hours, I sit there for 3 hours until the last 15 minutes before an exam, if something is due, and then everybody piles in. So let's try to be more constructive with these review sessions. I think they can be a great benefit if you guys get into them and ask questions. They don't have to just be about the homework. Shane Buchholz will be joining us on Zoom in the next couple days. He'll be our TA and he'll be grading most of your assignments. I'll be grading all of your exams though. So we'll get an introduction to Shane. And he'll set up some office hours and some Slack time. He'll probably do it with you over Zoom. So you'll have those resources as well. And I'll ask him to set up some Zoom office hours so that you can come in and ask him questions. Prerequisites, you need a probability class. You just have to have it. And so it's Statics 5104, or in VT it's 5104, but there's other variants. And ultimately, you should be at a reading level of Casella and Berger, which is our text. So that's right here. I didn't bring in my copy. Does anybody have a copy of Casella and Berger that they can raise up? It's a great text. There it is. Give it a turn, too. What a great cover. So that is awesome. So anyway, that thing's been circulating all over the world for at least 20 years. People have been using this thing. It's got a good balance, but it's all over the place. And I found it's difficult to discuss inference and come up with like a sequential sort of way of explaining everything just right, because you make choices. Then you have to come back around and amend those choices. And poor Casella and Berger have to do the same thing. So I sympathize with them. I think it's the best book going in terms of inference. So chapters 1 through 5 you should have covered. I know that Leanna in her probability class doesn't touch much of 5, so we'll be picking up with that. Here's your grade breakdown, 25, 25, 25, 25. So 25% on homework problems, and then equally split over the exams. So no big wallop on any one of those exams. This is nice and steady, everything is cumulative. If you have any questions about grading, just come and see me. But basically this says, if you go to your friend's homework and they got marked off a ½ point different than you, and you're really bothered by this, it will make no difference in your grade whatsoever. I would never do that where all of a sudden somebody's off by 0.4 and I change their grade. I look for clustering phenomena. So groupings. I can make questions as hard as possible, and maybe the top grade is like a 4. It's not going to be like that. It's probably going to be attainable if you get 100 on exams, but you know the drill. So if it bothers you so much and you want to talk about that ½ point, come and see me and we'll correct it for you. Okay. I think we just have a minute left. So I think what I would like to do, one more thing. One more link that's extraordinarily important for you. It's the schedule link. You'll click on that. And I've actually loaded this up for you. We'll pick up on this next time, but it says get started on 5.1 and 5.3 in Casella and Berger. Just read it. So read in advance. Even if you don't get it, it'll help you to know what's going on. So reading, coming back, that's how learning is done. Repeating, kind of a frequentist thing. Although I'd argue everybody is Bayesian. So it's kind of interesting. I do have some homework problems due on February 6th. You can get started on those if you want. I've also asked you for next Friday to define classicist, frequentist, Bayesian, and fiducialist. You're just going to write me a one-pager, 1 or 2 pages on definitions. And they don't have to be right. You can grab them from dictionaries. If you do write complete sentences that appear in some text, cite it. So otherwise, paraphrase it yourself. So, but if you do plagiarize, cite it, and now it's not an academic offense. If you do copy something, I will catch you. It will be clear to me as I read them. So, and I'll have a conversation with you on this, but don't do that. So it's just bad practice. So you'll define those things, and throughout this class, we'll get a better understanding of these various definitions. What I do want to show you real quick is a little bit more about this uniform example. And I've coded this uniform example up for us. And I'll be sharing this code with you, but we'll be looking at this next time. But what I'm going to do is I'm going to sample from this uniform distribution n times. And my n right here is 20. And instead of encoding theta, I use the symbol A. And it's 100 right here. And I've coded up a bunch of different inferential techniques down here at the bottom, and it prints out how close they are in average. And I want to discuss these techniques briefly, but there's an array of different techniques. There's some frequentist techniques in there. There's some rather ad hoc techniques that I've had students come up with that said, hey, how about this technique? And it's like, it's the worst one in the list. So, and we try to figure out what are our properties so that we know how to do inferences. And there's some Bayesian techniques in here. But ultimately, I call this thing range and mid-range, and we'll see why later on. But the range of the data and the mid-range, if I plot those two things next to each other, so what I've done is I've simulated this over and over and over again. So for each draw of n data points, I computed the range. It's the max minus the min. And I computed the mid-range. It's the max plus the min divided by 2. So it's somewhere in the middle. And it looks like this. And we'll confront this distribution later on. But it's an odd-looking distribution. Strongly triangular, those lines are strict. No data point is going to fall over the other side of that line. So kind of interesting. And there's lots of different ways to try to compute what theta is. In our case, I called it alpha. And here are a lot of different techniques for computing alpha. So I've done different things. I've looked at the range. Maybe the range has some information about what theta is. So if I take the max minus the min, maybe that's close to this value. And for all of my different realizations, repeating this, I've plotted a histogram of it. We know what A is. It's 100, and everything stacks to the left-hand side of that. So it's an estimator of A, and it's okay. There's another one. I've looked at the mid-range times 2, and it lives somewhere around 100. There's 100 for all of my realizations. And I have some other techniques. And so we're going to talk about those techniques. And they kind of all estimate the endpoint in lots of different ways. And some of these techniques are better than other techniques. And so I want to spend a minute next time coming back, talking about what these techniques are to motivate us to think about this is a hard problem. And unlike probability where there's answers, like if I ask you what's the mean of the distribution, there is an answer. If I ask you what's the best technique for estimating theta, there is no answer in this case. There's lots of different techniques, and it depends on how you're going to measure your correctness. So it depends. In probability classes, there's real answers. And in inference class, there's approximate answers, and some answers are better than others. We need to be able to quantify that, and even quantify what we mean by that. So with that said, that's all I have, and I'll see you guys on Friday. If you have any questions, I'll stick around for a couple minutes.